Hi, my name is Megan Hewell and I'm a PhD student at UCL's Mullard Space Science Laboratory in the UK. I'm part of an international consortium who undertook a multi-wavelength campaign using 6 space observatories, observing the Type 1 Seyfert galaxy NGC 5548 from June 2013 to February 2014. Our observations didn't show us exactly what we expected to see, so over the next 6 minutes I will introduce and explain what surprised us about the data we collected, the analysis we did, and the conclusions that led us to. If you want to find out more about this work, the first paper from this campaign is published at the link you see now. Using observations from XMM Newton, Hubble, Swift, NuSTAR, Integral and Chandra satellites, we plan to calculate distance constraints for the components of the absorbing outflows, called warm absorbers, previously observed in NGC 5548. But when we collected our first data, simultaneous observations from XMM Newton and Hubble, we had a huge surprise. As you can see from this plot of flux against energy in the X-ray band, the soft X-ray flux in the first observation was 25 times weaker than in the typical median observations taken by Chandra in 2002. This suppression continued throughout all 14 XMM Newton observations in our campaign. Thermal Comptonization processes, commonly believed to explain the X-ray spectra in Seyfert galaxies through multiple scattering of UV photons off hot electrons, cannot explain the shape we see. Therefore, it is much more likely that obscuring, partially covering material is absorbing the continuum. This obscuring material must be inside the X-ray narrow line region because the narrow emission features are not suppressed compared to historical data. 6 of our 14 XMM Newton observations were taken simultaneously with UV spectra using Hubble's Cosmic Origin spectrograph. The UV data shown here in a plot of flux versus wavelength shows many narrow absorption lines at the same velocities as previously known warm absorber components, but from gas with a lower ionization. This shows that the warm absorber is now being irradiated by a lower level of ionizing flux from the central source. These are not the only absorption features we see in the UV. There are also broad, blue-shifted absorption troughs at ionization levels similar to those needed to explain the X-ray obscuration. The strength of these individual absorption features are correlated with the strength of the X-ray obscuration, indicating that this UV absorption and X-ray obscuration is from the same photoionized gas. As we can tell from the UV spectra, the new obscuration lowers the ionization of the warm absorber components. This lower ionization also means the warm absorbers become more opaque to X-rays. Therefore, to model the obscurer correctly, we need a new model of the 2013 warm absorbers. With this new warm absorber model, we found that 2 obscuring components are needed to fit the data properly. The 2 obscuring components are both partially covering, one is ionized, while the other is almost neutral. The need for 2 obscuring components, rather than just one, is constrained by the unobscured high-energy data, showing the importance of a multi-satellite campaign to the analysis of these results. Using light curves from another satellite, Swift, we can gain an understanding of how long this obscuration has been going on. Looking at the data from 2005 to 2007, we see the hardness ratio, defined here on the left, as a normal value, shown here by the horizontal dashed lines. The higher hardness ratio, during 2012 to 2014, despite the hard X-ray flux staying consistent, indicates the obscuration of the soft X-ray flux has been ongoing over this period. So what else do we know about this obscurer? As the obscuration reduces the ionization of the warm absorber outflows, we can conclude it is closer to the source than these outflows are, giving us an upper limit to the distance of 10 to the 17 meters. The obscurer partially covers the broad UV emission region. Therefore, we can also conclude it is further out than the broad line region, giving us a lower limit to the distance of 10 to the 14 meters. The velocities observed in the UV absorption and the ratio of X-ray to UV covering factors also support a location just outside the broad line region. Finally, we see variations in the obscurer between XMM Newton observations of only 2 days apart. And, at the distances I've just mentioned, the velocity needed for the obscurer to cross the X-ray source within this timescale is of same order of the magnitude as the line-of-sight velocity of the obscurer we see from the UV. Therefore, the long-lasting nature of this obscuration indicates the obscuring material may be undergoing replenishment, potentially from the accretion disk or the broad line region. This obscuration, which we have detected and analysed from simultaneous X-ray and UV observations, has given our consortium a greater understanding of the geometry of the AGN in NGC 5548. We have an animation of this region at the link on screen for you to enjoy, created by Renaud Person, one of the world directors of the famous Assassin's Creed video game. Over the last few minutes, I've given you a brief summary of our consortium's first results from our observing campaign of NGC 5548. For any further information, the details of this analysis are in our paper. Thank you for watching.